Dear student, myself Dr. Surekha Jaiswal, Head Department of Physics, Moreshwar College, Bhokardan, District Jalna. Today we will see mechanics, properties of matter and sound. Course code number Phy101, semester 1st. Now, today's topics are difference of pressure across curved surface, different cases of film, first soap bubble or spherical film, second solid cylindrical film, and third hollow cylindrical film, and determination of surface tension by Jager's method. Now see, difference of pressure across curved surface. Now consider spherical liquid drop at rest and the inward pressure due to surface tension is balanced by equal pressure acting outward direction. Now see, to find the expression for excess pressure, consider a curvilinear rectangular element P1, Q1, R1, S1 enclosing a point V. The arc P1, Q1 is of length dl1 and having radius rm with center at O1. The arc Q1 R1 is of length dl2 having radius rn and center at O2. If the angle P1 Q1 is equal to delta Q1 and angle Q1 O2 R1 is equal to delta Q2, then radian and then initial length of arc P1 Q1 is M1 equal to Rm delta theta 1 and initial length of arc Q1 R1 is N1, that is equal to Rn delta theta 2. Now initial area of this curvilinear rectangular is A1 equal to delta L1 delta L2 and A1 equal to Rm delta theta 1 into Rn delta theta 2. So now if liquid surface is pushed outward along the normal at V through distance delta x by keeping distance same between initial and final position of two planes, then therefore final length of arc P1 Q1 is M2 equal to Rm plus delta x into delta theta 1 and final length of arc Q1 R1 is N2 equal to Rn plus delta x into delta theta 2. Therefore final area is A2 equal to M2 N2 equal to delta theta 1 into delta theta 2 into Rn plus Rm delta x plus Rn delta x plus delta x square, and that is approximately equal to delta theta 1 into delta theta 2 into Rn plus Rm delta x plus Rn delta x. Now neglected delta x square, which is very small, and therefore increase in area is given by A2 minus A1 equal to delta theta 1 into delta theta 2 into Rn plus Rm delta x plus Rn delta x minus Rn into delta theta 1 into delta theta 2 is equal to delta theta 1 into delta theta 2 into Rm plus Rn into delta x. Therefore increase in surface energy equal to T into delta theta 1 into delta theta 2 into Rm plus Rn into delta x Since increase in surface energy per unit area is called surface tension, and let P be the excess pressure on the surface at equilibrium, then outward force on it is equal to force equal to pressure into area, and that is equal to P into Mn equal to P Rm delta theta 1 into Rn delta theta 2, and therefore work done equal to force into displacement equal to P Rm into delta theta 1 Rn delta theta 2 delta x. This work done is used to increase surface energy. Therefore, from equation P Rm Rn delta theta 1 delta theta 2 into delta x equal to T into delta theta 1 into delta theta 2 into Rn plus Rn into delta x, and therefore P equal to T into Rm plus Rn upon Rm into Rn, and therefore excess pressure equal to P equal to T into 1 upon Rm plus 1 upon Rn. And if center of curvature lies opposite side of surface, then above equation becomes P equal to T into 1 upon Rm minus 1 upon Rn. Now see different cases of film. Now first, that is soap bubble on spherical film. Air is pressure on both sides of soap bubble surface. It means there are two free surface for soap bubble, so excess pressure is double for it, and therefore P equal to 2T into 1 upon Rm plus 1 upon Rn. Therefore, but for spherical surface Rm equal to Rn equal to R, and therefore P equal to 4T upon R. And for solid cylindrical film with single surface, for solid cylindrical film, the radius of surface is infinity, and radius of the surface is equal to the radius of cylinder, and therefore P equal to T into 1 upon infinity plus 1 upon R, and that is equal to P equal to T upon R. Now for hollow cylinder film, since hollow cylindrical film has two free surface, so its surface tension is double, and that is equal to P equal to 2T upon R. Now see determination of surface tension by using Jager's method. Now here this method is based on principle of excess pressure inside air bubble. Now principle, the excess pressure inside an air bubble is greater than the pressure outside it by 2T upon R, where T is the surface tension and R is radius of bubble. Now what is principle? The principle, the excess pressure inside an air bubble is greater than the pressure outside it by 2T upon R, and where T is the surface tension and R is the radius of bubble. Now see in figure, Jager's apparatus consists of, see, that is wool bottle, and this bottle has two openings. See in figure, this bottle has two openings, this one and this is another opening. One opening is fitted with the dropping funnel. See, that one opening of this bottle is fitted with the dropping funnel. See, through a stopping cord, that is a stopping cord denoted by K. In the other end, see here, in the other end of this bottle is connected with a tube. See, it's connected with this tube. Now, generally, the bottle containing a liquid which is water, here that liquid is here, that is a water, and this dropping funnel also has a liquid which is also water. See in here, that is shown in figure, that funnel is also consists of a water as shown in figure. At this end there is a manometer. See here the tube, here connected a manometer, and manometer consists of liquid having low density. At first limb of manometer and second limb of manometer, the difference between the liquid level in both manometer is measured by the help of scale. See in figure. Now, end of this tube, it consists of fine capillary. See here, at the end of this tube there is a fine capillary tube, narrow tube, which is dipped in liquid. That capillary end of this capillary tube is dipped in here in the liquid, whose surface tension we have find out. Before attaching this capillary tube with this apparatus, we find out radius with the help of travelling microscope, and this stopping cork is used for adjusting the height of beaker. Now, in this method, a funnel with control knob C, that is a K, is inserted in the bottle. Now the bottom end of funnel tube is closer to lower end of bottle, and another L-shaped tube is also inserted in same bottle, but its one end is closer to the rubber cork of bottle, and another end of this L-shaped tube is connected to T-shaped tube. See here, and lower end of T tube is connected to a manometer here, that is a manometer as shown in figure, and other end is connected to vertical capillary. Another end is connected to this vertical capillary tube which is dipped in the liquid, and this capillary tube is dipped in experimental liquid whose surface tension have to be measured. Cap is beaker. Now the rubber cork keeps the bottle as airtight. Let manometer is filled with liquid having density rho 2. See, in the manometer there is a liquid that's having the density that is denoted by here rho 2, and density of liquid kept in beaker is rho 1. See, that liquid having the density that is denoted by rho 1, that is in beaker. The lower end of capillary tube, that is point A, this is lower end of the capillary tube denoted by the letter A, point A, is at distance HL. See, the height from this point A to this surface, that is denoted by HL, from liquid surface placed in beaker. If knob K of funnel is slowly open, see, the knob K is slowly open, then what happens? Such that water from it descend drop by drop in big bottle. then this water is here that descend drop by drop in big bottle. Since this bottle is made airtight, so pressure inside bottle increases, which can measured by using manometer tube M. And the flow of water through funnel is so adjusted that the air bubbles are formed periodically at the lower end of capillary tube. Now measure height difference in manometer. Let it will be HM. It is denoted by this height difference is denoted by here HM, and at the moment of forming air bubble, the pressure inside capillary is equal to atmospheric pressure, that is denoted by P0 plus HM rho to G, that is P0 plus HM rho to G. Since air bubbles are formed at the end of capillary tube, so pressure inside air bubble is 2T upon R plus P0 plus HM rho 1 G, where R is the radius of capillary and rho 1 is density of experimental liquid in beaker. At equilibrium, both pressure must balance. So using equation P0 plus HM rho 2 G equal to 2T upon R plus P0 plus HL rho 1 G, and therefore 2T upon R equal to G into HM rho 2 minus HL rho 1, and therefore surface tension T equal to Rg upon 2 into HM rho 2 minus HL rho 1. And this method is simple but gives good result only when the radius of air bubble is equal to the radius of capillary tube. Thank you.